Okay, I think it's done. Oh.
I don't want to see the answer.
Okay. Okay, so we're ready to begin this session. It's my pleasure to introduce Professor Keith W. Hipel from Systems Design Engineering, professor at the University of Waterloo. He's an adjunct professor, but also distinguished professor emeritus. He leads the conflict analysis group. He's former president of the Academy of Science within the Royal Society of Canada, senior fellow of the Center for International Government's Innovation, fellow of the Waterloo School of International Affairs, and his research interests fall within environmental system science and engineering. Professor Hipel has received many honors, including he's an officer of the Order of Canada, Killen Prize in Engineering, Japan Society for Promotion of Science, Eminent Scientist Award, Joseph G. Wool Outstanding Career Award from the IEEE Systems Man and Cybernetics Society, the IEEE Systems Man and Cybernetics Society Norbert Wienert Award, and so on. Please, there's a lot more, but I think that you get the idea. So please welcome Professor Hipel.
Yeah, thank you, Christopher, for your introduction. Hello, everybody. Who are students here? Which ones are students? Okay, great. And the rest, I guess, faculty and staff. Yeah. Okay, well, this is my first time I've given a lecture in 4 years. I had a stroke about 4 years ago, 2 very bad ones, but luckily I recovered and through exercise and better diet, getting better and better. So it's real nice to try myself out again. So since I'm finally in a class again, there are some students here, but we got to have a test, right, profs? Got to have a quiz. So let me start this out with a little quiz. Since this is, I guess, the Fields Institute combined with WEC, let's have a mathematical quiz. Who is often referred to as the father of geometry and author of the ancient work Elements, which was used in mathematical instruction up to the 20th century, until the 20th century. Anybody can play. Who said that?
Somebody good.
You're right, yeah. Please come up to the front here. You get a prize, yeah. 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 Yeah, congratulations. Tell us your name and your research area.
Thomas, I'm in engineering.
What type?
ECE, cryptography.
Cryptography?
Yeah,
Okay.
it's kind of different from this. So I'm working on like a specialized communications medium.
Right.
Because like I guess like Marshall McLuhan said, the medium is a message.
Right, right.
And famously,
To see the name again.
and basically and like I just I'm working on like a simple medium using both like kind of like a peer-to-peer architecture.
Okay. And who is your supervisor?
I'm this case, so I'm like master's student.
Okay, very good. Okay, well, let's give the clock. Good luck in your research. Thank you, Thomas. Yeah. Okay, so you got that right. Very important here at Waterloo, cryptography. Part of the quiz later, we'll deal a bit with that. Okay, who introduced the decimal positional number system to the West, as well as the terms algorithm and algebra? Yeah, go ahead.
Am I allowed to? Al-Khwarizmi?
Go ahead. Who?
Al-Khwarizmi.
Yeah, you're right. Can you say the whole name?
Muhammad ibn Musa al-Khwarizmi.
Right, okay, great. Come on up here.
Oh, sorry.
I'll put this over here.
Expect primates stepping over the table.
Okay, well, there we are. Congratulations. Well, you get a pen too.
Oh, thank you.
Just a minute.
Never been there.
What color? Green? Okay, sure. Sure. Now you gotta try some color here. You can pull that out.
Okay.
Okay, tell us about your area of research in Christopher.
Complex systems, applying mathematics in unexpected places. Algebraic automata theory, but also artificial life. And I'm going to talk here about carbon currencies.
Carbon currency. Okay, so let's have a round of applause.
Thank you.
So 1-1, now it's time, props versus students. Okay. Yeah, so as you know, the Persians developed a lot of ideas in science and mathematics. I have a good friend, Mo Jamshidi from the United States. He was going to write a book about Persian science. And I keep telling him, write a worthwhile paper. I've seen enough of your technical papers on large scale systems. But it's quite a history, quite an illustrious history. So let's try another one here. There. So algorithm is the last Latinized version of his name. And algebra is Latinized version of algebra from the title of one of his works. So really contributed a lot to humanity, this gentleman. Here. This doesn't seem to be working. Okay. Who invented Cartesian coordinates?
Come on, students.
René Descartes.
Oh, yeah, right, okay. Yeah, please come up here. René Descartes, there we are. Okay, great, congratulations.
Yeah, thank you.
Please introduce yourself.
Oh, hi, I'm Deirdre Haskell, and I work in mathematical logic, specifically model theory, and I'm the deputy director of the Fields Institute, which is why I'm here today.
Oh, okay, well, very nice to meet you.
I had to say that. I'm sure.
What color pen would you like?
I'll go for green one as well.
Green, okay. Green's popular. Yeah. Well, I think that's a real nice combination, Fields Institute with Ishi, because I'm a real fan of mathematics and mathematicians. Once you can attach mathematics to it, then of course you can develop, you have a lot of really good sense you make out of whatever you're doing. Then you can develop a decision support system and make your decision technologies available to others. So extremely important. What a nice marriage of ideas at this conference. So who invented the mechanical calculator and collaborated with Pierre de Fermat in the development of probability theory? Who? Couldn't hear you. These?
Oh, no.
I don't think you said this. I'll give you the answer. If you did, so Blaise Pascal. We actually had the Pascal lectures at Waterloo. How many have been to a Pascal lecture? They usually bring in really good speakers over the years. Okay. Who invented infinitesimal calculus?
It's
Who? Leibniz, right? Yeah, right. Yeah, please come up here. I'm glad you did it in that order because most people say Newton first, but Leibniz actually had more impact. Okay. And your name?
I'm Ali Reza.
Nice to meet you.
Nice to meet you.
Congratulations. What color pen would you like here?
Everyone wants the green.
Well, we got purple too. You're in which department then, Reza?
I'm in civil and environmental engineering department, but I'm not a civil engineer.
You're a mathematician?
No, I'm an industrial engineer.
Industrial engineer.
Yeah, we work with a lot of this.
Right.
Like,
But you're a Persian?
I'm a Persian.
Yeah. Okay. What color pen would you like here?
Since we're going to go out of green, I go to blue.
Okay. Here's a nice blue one. Well, that's a nice green color too, in a sense.
Thank you.
Okay, you're welcome. Okay, tell us about your research, please.
So at our lab, we try to connect environmental impacts of air quality and climate change policies to human health and try to create monetary values for them and to inform policies.
And sorry, Mary, that was which department?
A civil and environmental.
Or civil environment, who are you working with there?
I'm working with Dr. Rebecca Soy.
Very good. Okay, well, let's hear it for Amir then. Keep up the good work.
Thanks.
Okay. There's quite an interesting story here. Leibniz and Newton both independently developed calculus. Now we got something to learn from both of them when it comes to research. What is it about Leibniz's calculus that was superior to Newton's? Leibniz is below from the left here.
Notation?
That's right, exactly. Very good notation. Leibniz had a much better notation. That's the notation, of course, that we use today with the differentials. Whereas Newton had that capital D, I remember, for a derivative. But there's something I really liked about Newton. He used the need for practical applications to develop his theory. So for example, his real interest was physics. And he had an intuitive idea how he thought physics works. And he knew that somehow he had to be able to model mathematically the rate of change. So he developed calculus to solve a practical problem. And so to the mathematicians in the room, there are a lot of really tough practical problems to solve in climate change. So we need a lot of good mathematicians. So there you go, follow in the footsteps of Sir Isaac Newton. That's what he did. Who invented the concept of a function and introduced or popularized the mathematical symbols f of x, pi, I, e, gamma, and sigma? Mathematicians really like this chap.
Gauss?
Not Gauss, but I'm a fan of Gauss too. I really like Gauss. And he's also from a German-speaking country.
Euler.
Euler, that's right. Yeah, there we are. Leonhard Euler, Swiss. So Chris, that was you, or was it you, Counselor? Chris, come up here.
I already have a pen.
You can get a pen for your wife.
Oh, okay. We should get a purple one.
Okay. Okay, very good. Congratulations. I like Euler a lot too. He's a great mathematician. Who pioneered the application of operator theory to quantum mechanics and inspired by the game of poker was a key figure in the development of game theory?
I'm gonna guess Von Neumann, but it's probably wrong.
That's exactly right, Don. Please come up here. Von Neumann, he's one of my favorites. John von Neumann. Yeah, so nice to see you again, Don.
Yeah.
What color would you like?
I'm sorry, but I want the green one.
Okay, yeah.
Yeah, or maybe the blue one. I'll just,
The blue
no,
one.
I got the green one's easier
Yeah,
to
that's
fold.
fine.
It says
Okay.
little,
Okay, Don, and tell the group about your research, your current position.
professor in the School of Planning, secretly an economist. I was excused from the fold, and right now we're focusing on development of agent-based land and housing market models, and also understanding the environmental impacts of residential landscaping. And then probably something else I forgot. Yes, thank you.
Well, thank you.
Yeah.
Don was director of Wiki for how many years?
4.
I think you were one of the founders, right? And then she
More or
was great.
less. I'm that person behind the scenes that still tells everybody else what to do, even though I don't have an official title. Yeah.
I know.
Yeah. Yeah, nice to see you again, Don.
Yeah,
That's
it's great to
great.
see you. I'll give the pen back.
Here he is right here, John von Neumann. He's one of my favorite mathematicians, very popular with engineers. Does anybody recall the title of the famous book he and somebody else wrote and the co-author?
Oscar Morgenstern.
Yeah, you're right. Yeah, come up here, Christopher. How many children do you have? Okay.
More pens.
But the title of the book.
Yeah, it's like. I can't actually know, I don't actually know the kind of. Theory of games and economic behavior.
Exactly, yeah. Very good.
Yeah, I tried to read that.
John von Neumann and Oscar Morgenstern. Okay, what color would you
I'll
like?
get a
this?
blue one.
Blue one, okay.
Okay,
Okay, great.
I'm cheating because I am a mathematician. So.
The 3 strikes are out for you can't.
Okay, thank you.
John von Neumann. He was Hungarian, he was born in Budapest. And actually, the apartment that he lives in is now a bit of a museum, but he's very popular with engineers, John von Neumann. And he actually died of cancer, but does anybody know why? Sorry,
Is it radiation, or radioactivity?
who said that? Oh, yeah, that's close enough. So you win again, come up here. So if you have a wife or a girlfriend, then give me luck. Come on back up here. How did he die of radioactivity?
I think he was working on like the Manhattan Project. Or, you know.
Go ahead. Now, they used to take some of the famous scientists and mathematicians to watch the explosions in America. Yeah,
No,
come on
Los
back up
Alamos,
here.
yeah.
Okay. I mean, there is a goose that is very aggressive, but it's quite.
What would you like? What color?
Okay, I guess I'll take the,
So it was a mirror, right?
Thomas.
Tom, sorry, Tom. Tom, right, okay, great. Okay, now we're getting closer to cryptography. Who is widely regarded as the father of theoretical computer science and artificial intelligence, and played an instrumental role at Bletchley Park in breaking the Enigma code?
Imitation. I know the movie.
Yeah, that you got the movie. Remember the name of the person?
Can we give a hint? Oh. Okay, can we give a hint to, he has a test named after.
That's right. Okay.
Yes.
Yeah, he got
I
it.
can.
Oh, yeah,
Next
you got it. Wants to come up here, that's right. Well, now the persons are cleaning up what they learned 1,500 years ago, they still remember, I guess. Okay, congratulations. What color would you like?
Just black.
Okay, great. Tell us what you're working on for your research.
I'm working on climate change mitigation, specifically on a technology called reactor capture, which sucks CO2 from the air and from the ground. And I'm working mostly on the policy side of that technology and how we should make the decision under deep uncertainty. Yeah, and my supervisor is Professor Hipel and the specializer.
Yeah, very important research topic. If they get out of hand, we gotta extract directly from the atmosphere, the carbon grams. Yeah. Okay. Okay, great. So here's right here, Alan Turing. So brilliant man. He ended up after the war at the University of Manchester, or it was probably called UMassing, University of Manchester Institute of Science and Technology. But there he is in a small park in Manchester. So he's all alone there. So I thought I'd go over and say hello. See how it was. How many have seen that statue in Manchester? It's a little park not too far from the university. And that's a Hungarian friend of mine, Imre Rudas. He's president of a small university, small technical university in Budapest. So we were speaking together there with Turing. And there you see he's holding an apple. Because he was so badly discriminated against, he got highly depressed and he committed suicide. He put cyanide in an apple and then he ate the apple. And guess who copied that?
Where's the sign right now?
But the movie, how many have seen The Imitation Game? I'm trying to figure out why did they call it The Imitation Game?
Because of the Turing test? Well, one of the tests.
Okay, maybe that, yeah.
I
Okay,
think the suggestion was that Turing himself, as probably somewhat autistic, was trying to imitate a human being because he didn't know how to be a human being. In the same way that a computer tries to imitate a human being with the Turing test.
right. All right, thank you. Which country achieved initial successes in deciphering Enigma code before passing on their work to the British? No, Turing was from the UK. So it's not England, it's another country. They were ahead of him. There's actually a movie about this. British secret agents went right across Germany before World War II on German trains to this country. They're actually, yeah, that's right, Poland. There are actually 3 Polish scientists. Here they are here. I gave this talk once in Warsaw, so I had to, of course, bring Poland into it. I had a meeting with the president of the Polish Academy of Sciences. How many have seen the big birthday cake in Warsaw, that huge Soviet era building? It's just massive, right in the middle of Warsaw. It's still there. Okay, now we're getting closer to home. Who cracked the Lorentz code? More difficult than the Enigma. That was used by Hitler and the German High Command for high-level strategic communications at Bletchley Park. Made major advancements in graph theory and moved to the University of Waterloo in 1962. Who said that? Yeah, you're right. Come on up here. You just have one wife, right? They're here for one of your children. Pick another pen, please. Yeah, so it's William Tutt. That's correct. There he is right there. One of the most famous mathematicians ever to come to Waterloo. Now, what was the most decisive battle of World War II in the German-Russian War? Kursk, that's right, exactly, Kursk. More important than Stalingrad. And actually at Kursk, K-U-R-S-K, they had broken the German code, so the British were telling the Russians all the moves of what the Germans were planning to do in the Kursk salient. Okay.
University of Toronto, sorry, that's down.
Yeah, University of Toronto, yeah.
Vienna.
Yeah, so Waterloo now has the highest concentrations, of course, and it's very famous for its cryptography institute. Who was studying cryptography? Was that you, Thomas?
Yeah, and so this is, it's like, I think, yeah, we're like in combinatorial optimization. I think we're like one of the few schools in like North America that have like the science.
Yeah.
The department of combinatorial optimization.
Yeah, very important area. And then climate change is going to become very important too, because there'll be so much data that has to be collected by the different countries to show they're abiding by the international agreements. And then somehow breaking into their data or intercepting messages could be important. Now, I think that he's probably the greatest Canadian war hero from World War II, William Tutt. And how many have seen his grave? Anybody seen it? Who's heard of West Mount Rose? That's where the covered bridge is. It's a little Mennonite town just outside of Waterloo. You go to see the Mennonite bridge there, the covered bridge. There's one church, just one little United church in the town. Go directly behind it, you'll see the grave site of Bill Tutt. So it has a nice peaceful rescue there. No one accomplished so much in life. Okay, so I think there. So I guess that's the end of the quiz. Yeah.
Switch to the other.
Well, I switched to the other speech. Yeah, that's not this is that one there. Got that one there. Okay. Now for this one, I have a copy of a paper that we published. And I'll personally pass it out because you're allowed to give a personal copy of the copy. You want just because you're me.
Sure.
This is a personal copy of everybody if you'd like one.
Yeah.
So climate change, as you know, involves a lot of conflict. And we were very interested in environmental conflicts. And there wasn't really a good game theory technique available that you could apply directly to strategic conflicts. And I think you'll see the reasons why as I go on with the talk. So this is the paper that I wrote with 2 colleagues, Mark Hilliger and Diping Fang. You can see their co-authors there on the paper. And actually, this was one of 4 or 5 talks that I gave across Canada. I won something called the Romanowski Medal from Royal Society of Canada. And part of that award, it actually has, there's funding there to pay for a lecture tour. They want, whoever wins it, they want them to spread the message around. That was quite nice. Now, Romanowski, he was a meteorologist. He worked in the theory of measurement for the National Research Council of Canada. And at that time, he was very concerned about nuclear war, it was Cold War days. So he started this medal for research in the environment. And little what he suspected is come back now like a war in the nine, this demon from the past, because of the Russian behavior in Ukraine and elsewhere. So that's really sad that that's occurring. Now there's another medal, since we have the, let's see, the Fields Institute here. There's one called the Singe Medal. That's a medal the Royal Society has for mathematics. So I strongly encourage you to nominate people for that award, because they want to get good nominations. SYNGE. I think he was a mathematician at the University of Toronto many years ago. So what I decided to give today then is an overview of the work we've done with this graph model. We wanted something that can work well in practice. And the order of the presentation is the same as the order of the paper. Did everybody get a copy of the paper who wants one? Okay. So we were asking the question, how can water resources and environmental controversies be resolved? And like I say, there wasn't a methodology from game theory available that could apply directly to those problems. So we designed something, eventually we called it the graph model for conflict resolution, to get strategic insights into conflict so you can hopefully make better decisions. So the purpose of this talk is to put it into perspective. So I'll try to point out the fundamental design associated capabilities by going through the historical development. Now you can see the little pointer there, can you?
Yes.
So this is a genealogy graph that I drew. That's given in the paper there, I think about page 14. So up here, let's call them game theoretic methods. On the right here, I call it quantitative preferences, and over here, non-quantitative. So here we have techniques that they sometimes call classical game theory. There's cooperative game theory, extensive form, normal form, agent, and more recently we have these agent-based models. So over here, in order to use a lot of these techniques, you have to have cardinal utility functions, and that's why I took the word quantitative. Whereas over here, it's just relative preference information. So Christopher may ask me, Keith, after your talk, I'd like to take you for a tea or coffee. Would you like coffee or tea? Well, I'd probably say, well, at this time of the day, I prefer to have tea, thank you. I probably wouldn't respond saying that coffee's worth 9.6 and tea's worth 3.7 at the present time. You say, oh, you can get your own tea or coffee. That's how I'd respond. But that's the type of information they assume with a lot of these methods over here. Now, we've used some of these techniques too in some of our research in water and the environment, but not for strategic conflict. They don't work there. So we've done some work in compliance problems, like with nuclear weapons. They want to check, are they cheating or not? And now this is a very big problem, of course, in the environment, the whole area of compliance, enforcement of environmental laws and regulations. You want to make sure that the people who sign the agreements actually abide by them. The trouble with some of these approaches here is they get quite complicated. Like extensive form gets complicated very quickly. So as I mentioned, in non-creative quantitative methods, relative preference, and over here we assume cardinal preference. Here we can handle any finite number of decision makers and options. Here often it's a limited conflict size, and they might compare expected utilities. Over here, we look at it more like chess thinking. Let's see. If I move here, my competitor may move there. So you might be a large company, let's say, that makes cars. Well, let me see. I'm going to reduce the price of this type of car. Then you ask the question, but what will my competitors do? Well, they may reduce the price of their cars too, and then you end up in a worse position because both sides then get less revenue from selling their cars. You got to think of the consequences of your move. So we think in terms of moves and counter moves, which is quite different from the methods over here. They often compare expected utilities. I know when I think of conflict, I don't calculate expected utility in my mind. Here, the order of movements is often important. Here, it can move in any order. So those are some of the key differences. The big one was the preference information assumed with these quantitative. Now, I should point out here that on both cases, both sides of this sheet here, they're highly mathematical. They're 100% mathematical. But as I just mentioned, the quantitative means for preference type, and the non-quantitative is just relevant preference. So there's something called metagame. I'm just going to go back a few slides again. I wanted to just go down. Let's just go down the left side here. So here we have down this branch here, we have metagame analysis. There's something called drama theory, where they model conflict like a drama. And here we have the graph model for conflict resolution. And we have a logical form to it, and we'll have a matrix. We have a matrix form to the model too, to write it down mathematically. And I'll say a little bit about that as we go along. But it has a good solid mathematical basis, everything here. And that's so important because if you have a good mathematical model, you can say a lot of things about the problem you're looking at that hopefully then is confirmed by data too. So metagame analysis started by Nigel Howard. There's his book down at the bottom. He was at Waterloo for a few years, but from the UK. Well, I'm going to show you this game here, shown in normal form. We elected to use a very simple conflict in this paper because we just wanted to get the basic ideas across. Like today was debating, I could have shown you a real complex real world problem. This could apply to many different types, including COSRA. Tell them about the problem you applied it to the graph model COSRA, just very briefly.
Yeah, I was when I had the conflict resolution course for the term project. I applied the same methodology on the carbon pricing debate between the federal government and Alberta. That finally they went to Supreme Court, and it was a multi-level game. So I just used this methodology for modeling that decision making.
And it worked out as a good multi-level game. Okay, great. Thank you, COSRA. And good luck in finishing everything. As you say, publish or perish. Yeah. So here's a very simple conflict. It actually has the same structure as prisoner's dilemma. That's a very small conflict to reflect. Should I cooperate or not cooperate with somebody else? So here, cooperate. The decision maker agrees to significantly reduce greenhouse gas emissions. Don't cooperate, does not agree to that. So here, very simple, two players, US and China. The US is the role player here, and China is the column. So here is C for cooperate. So if China chooses C and the US chooses C, we get this state here called CC. Here, if they cooperate and China doesn't, it's a state CP. And just to make the explanation easier, although it might seem confusing now, we give each state a number here, 1, 2, 3, and 4. Now these other numbers here represent preference. So the first entry is the preference of the US, where a higher number means more preferred. So here, the state DC, that's where the Americans don't cooperate. They don't spend much money in cleaning up, whereas China does. They're cutting back significantly on the greenhouse gas releases and spending a lot of money. So that's also the least preferred for China. Notice that has a 1. So this is relative preference because it's just an ordering of the states. Like I say, a higher number is more preferred. So think of them being ordered from most to least preferred in this case. So we call that orbital preferences because it's an ordering. So I'm going to use that as a basis of discussion just to keep it simple. Trouble is if I show a really complex one, is then we get bogged down looking at the details of the history and what happened in the conflict. Now, Howard looked at what he called the breakdown of rationality. So actually, rationality, Nash equilibrium, this predicts state. It fails to predict CC. So you look at these states here. Notice that DD, that's where they both don't cooperate. That only has payoffs of 2 and 2. Whereas CC has 3 and 3, so it's more preferred by both players. We call them decision maker. We like that word better. Now this one here, if the game were at DD, the United States controls movement in the rows. So if they went from a D to a C, don't cooperate to cooperate, they go from a preference of 2 to a preference of 1. So it's actually a unilateral disimprovement. Whereas take, and likewise, if China then, they could go from a D here to C there. So if they went from D here to C here, we get the state DC. They go from preference of 2 also to 1. So it's a disimprovement for them too. So there's no unilateral improvement by either player. So they probably stay there. And that's what Nash equilibrium predicts, DD. And you can see that it clearly misses the obvious solution here, CC, which is where they both cooperate. And then they both benefit a lot because the greenhouse gas cutbacks, a lot of serious side effects then are hopefully eliminated. So Howard then developed a number of stability definitions. I'll just say what they are verbally, but all of this is really moves and counter moves rather than taking expected values and that type of thing. So general meta rationality, every UI, that's unilateral improvement by the decision maker, can be sanctioned by counter moves of other decision makers. Like I say, that one car company reduces its prices for a certain model, then the other companies do the same. So they actually end up in worse position. They're better off not to move then. Symmetric meta rationality, each unilateral improvement by decision maker can be blocked by counter moves of the opponent, and the focal decision maker cannot escape. I can move its block, and then I can't escape from that sanction. So here, GMR stands for general meta rational, SMR symmetric meta rational. So here, for example, notice the US, if we were at CC, they could change their strategy selection here from cooperate to do not cooperate. And notice it goes from payoff of 3 to payoff of 4. So that's a unilateral improvement. It's more preferred for the Americans. Although I wish it weren't, but in this game that we set it up, it is. Now, once we're here, China could actually change from a C to a D and change their preference from 1 to a 2 and move the game over to DD. Now, DD, notice for the Americans, there's a 3 here and a 2 here. But DD is less preferred by the United States to CC, so therefore they're sanctioned. So that this is actually general meta rational. It ends up it's sequential too, because they're sanctioned by a unilateral improvement by China. So I hope that sort of comes through a bit there, that idea of moves and counter moves. So you can see that this normal form, that box-like structure there, is convenient for 2 decision maker cases, but becomes troublesome for conflicts with more than 2 decision makers. The hard proposed Austrian form, and let me show you this in table 2. And here we have 2 decision makers, US and China. Has one overall option, cooperate. Y here means yes, cooperate, no means no, don't cooperate. And China has the same one. So they have cooperate where they cut back on their greenhouse gases. And if we have the same 4 states here as we did have in the game in normal form, but it's written using this option form. Now you could actually extend this list on as far as you like, any number of decision makers and options. So the size of the game, well, it does become a problem later on in certain algorithms because we don't want it to be too big. So we're removing feasible states and things like that. But we can handle any sort of finite number of decision makers and options. So you can see it's a nice notation. Because you can say, well, what can I do? What can my opponent do? Those are the options. And then Neil Fraser and I, his PhD on mine years ago, we wrote a book on this we called it conflict analysis, where we extended metagame analysis. And as I mentioned, in the sequential to the stability, then I think I mentioned it briefly. That considers the idea of having credible sanctions. In other words, I'll block the other players improving as long as it doesn't hurt me. And that to us sounded very sensible. So here's the game in option form. And once again, let me repeat, every table and figure given in this on the overheads is also given in the paper there. Now, just to show you the movement here. So here we were at state, let's say Y, that was CC, yes, so you take cooperate. So the US has a unilateral improvement to here by going from a Y to an N. They move from state 1 to state 3, but then China, you see, could go from a Y to an N. to move the game from here over to here, and it's unilateral improvement for China. But 4 is actually less preferred than 1 by the Americans. So they end up worse off. So therefore, they're better off not to move. And China can block it without hurting themselves. When there's more than 1 UI, all UIs have to be blocked to induce SEQ stability. When there are more than 2 decision makers, credible sanction can be generated by UIs based upon UIs among the sanctioning decision makers. So you can see the way this can become complicated. You got to keep track of things. When there's no UI Nash stability, there is also SEQ. I was going to ask you a question, but I actually have the answer here, so I'll ask the question anyway. Now we have an existence theorem for SEQ. We can prove mathematically that it'll always predict at least 1 equilibrium. And why is that important? That's the nice thing about mathematics. You can look at the properties of the models you're developing. Why is it important that we predict at least 1 equilibrium?
So you can get tenure in the economics department? No, I'm sorry, I don't know the answer.
Well, the answer is something always happens in reality, even if it's all like nuclear war. So if you have a game theory method that can't predict an equilibrium, you should take a more serious look at it. Is it realistic? Yeah, this proof I think is given in 84 book. It does take a few pages to prove, but that's nice to know. We'll always get at least 1 equilibrium predicted, and they're usually more. They're often more than one, because often there's more than 1 political compromise solution to a problem. Now, this tabular form was a nice way to do calculations by hand. I won't spend much time here, but basically this says US has a UI from 1 to 3. China can go from 3 to 4, and notice 4 is less preferred than 1. So it's just a quick way to do hand calculations. Now, so you can see there, which you have to know, who are the decision makers, what are their options, what can they do, and what are their relative preferences. So preference information is always the one that's toughest to get. So we developed something called the preference tree. Now here the number stands for the option number. So what is most important for the Americans is that the Chinese take option 2 and cut back on the greenhouse gases. Most important for them is they don't take their first option, which to cut back. So if you follow this tree here, it ends up, this is the ranking of states for most of least preferred. And you can actually do the calculations as shown down here too. The higher level gets a higher weight, and the next level another weight. So if you're dealing with a client, you would ask them, what's most important to you in this conflict? Well, they would say, we'd like this to happen. And they might put conditions there too. We'd like this to happen if that also happens. And so you can take care of that using preference statements. And it's a really quick way then to order your states from most to least preferred. And then it also allows you to order some by hand, and some of them don't make sense. So in practice, we might want to know, what is independent behavior? How well can a decision maker do in a conflict when acting independently based on his or her own interests? And cooperation. Can I do even better by cooperating through others through joining a coalition? Generally speaking, the answer is yes, but not always. But we recommend checking for both. Because if you're going to do better working with others, then why not do it? Now, hyper kings. This is a situation where you have misperception. So let me just see here. So I might go over here to Chris. Chris? Okay, good, you responded correctly. Sometimes when I go like that to somebody I don't know, they think I'm going to hit them, they jump back. This thing's falling apart. It's almost falling apart. So you misperceive what the intention is of the other player, or one or more other players. Wait, thank you. Not working. Well, why would we need a phone there?
To call them to tell them the phone is broken.
Yeah. Let's tell them to get it right.
Still have to squeeze.
They're totally wrong.
It's two screens. It's to go up and down.
No, just open the first, you can just,
Open the.
yeah. and then you can-
What time was it in there? I don't think it's that long.
Hope I didn't call anybody.
It's gonna fall in after once.
Okay.
Yeah, so Chris may mistakenly think, for example, I prefer a coffee over tea when it might be the reverse, right? So often you have misperceptions about preferences and intentions. And Neil Fears and I, we did an analysis of the Cuban Missile Crisis in October 1962. We think it was the best analytical study ever done of the Cuban Missile Crisis, and it was a hyperdoom. The Russians under Premier Khrushchev did not expect the Americans to react as strongly as they did and have a naval blockade. And the reason for that was because Americans performed so poorly at the Bay of Pigs. So that's one level of misperception. And then we think the Americans were aware of that misperception by the Russians. So when you think of it as a hypergame, it gives a really accurate model of what happened in the Cuban Missile Crisis. So you could have any combinations of these misperceptions. And the answer how to solve these is quite simple. Even if they have a misperception, just analyze the game from the way they see it, even if it's incorrect. So there I mentioned different levels. The Cuban Missile Crisis was the second level. And you can apply this methodology using those solution concepts to any type of hypergame. Now I'm going to get into the graph model, which is an extension of the conflict analysis approach. We have two books on that, one in 1993, another one in 2018. Now the 2018 is by Springer Nature. If you're at the University of Waterloo, hopefully Toronto too, you can download this free of charge. This book, the second book here, got some nice explanation in the first three chapters of the book, and it's highly mathematical in the next book. And there I am with my co-authors, Haiyan Xu. She was a PhD student at Mark Hildebrand at 2011 or so. She graduated, and Li Ping Fang. He was a PhD student way back, who graduated in 1988. Now he's at Toronto Metropolitan University. So if you'd like a copy of it, this is a support system to use for research, just email Li Ping, he'll tell you how to get at it. So remember we had those states and the different cells in that box. Well, instead of a box, let's think of it as a graph. And each player can cause the game to move from one state to another. So for example, here, if the Americans go from cooperate to don't cooperate, you go from a C to a D, that moves the game from state 1 to state 3. They can move it from 2 to 4. And China can move it from 1 to 2 and 3 to 4. So there we are on the left hand, we have a directed graph of the United States. And the preferences are given at the bottom there, for most of these preferred for US here. Here it is for China. That's a directed graph. Now we can put the two together and we call it an integrated graph. You can imagine the real world if you have a very complicated situation. These graphs can get very messy. But the nice thing about graphs that I like, if you have a graph, it means you can attach mathematics to it, attach algebra and equations. So that's nice. So here notice there's a lot of information here. The movement of the two players and joint movements they could do. So whenever you have information in a graph, you can usually store it in matrices. So that's what we decided to do. So vertices represent states and arcs movements. Now you could have irreversible moves too. So for example, if it's a war situation, once you drop the bombs, you can't take it back. So and you could have common moves. So here, for example, if they go from cooperate, don't cooperate, we assume it'd be very difficult for the Americans to change their mind. So so we thought that was a bit like an irreversible move, but a better example is a military one I mentioned. So a common move, more than one decision maker can cause a conflict and move to the same common final state. So during the Cold War, either USSR or the United States could launch a nuclear attack. The final state is nuclear winter. The reason we do this is because we want to simplify the game. Sometimes they can get large in practice. We have practical ways for removing useful states. Now, the other thing we can do is we can handle intransitive preferences. At the top is an example of transitive. I prefer coffee to tea, maybe because it'll keep me awake, look better. Tea to Coke because it's healthier. And then you might assume you prefer coffee to Coke. That's transitive preferences. And intransitive, we might prefer Coke to coffee. You might prefer Coke to coffee because you prefer at this time to have something cold, for example. Well, you want to have a game model that can handle transitive preferences. Why? Because they happen in practice. So I don't think they should be discarded. Of course, if you have a utility function, there it's automatically assuming transitivity. And we think that's a little bit naive for some conflicts. So it's the decision makers' value systems that determine interactive moves and counter moves among decision makers. And they're expressed as preferences among states and then conflict. So I mentioned these already, so I won't spend too much time here, but just looking at the states. Most important to them is that China selects option 2. So China pays for an expensive cleanup. And they prefer one where they don't clean up. And China has a similar one. You know, quite often you can have preference uncertainty. So we have a number of ways for modeling uncertainty of preferences. This first one is quite clever. Kevin Lee, another PhD student of mine, he said, well, the type of uncertainty is unknown. You don't know what the preferences are. I don't know if you prefer coffee to tea, for example, right? So you just don't know. And we could use fuzzy sets. You more or less prefer one state over another. Gray sets, where you have numbers and interval numbers. And probabilistic, where you have probabilities attached to the preferences, or any combinations of the above. And then we looked at something else called the degree of preference. I may be a very avid environmentalist, and I greatly prefer that this company clean up its pollution. So it's like a type of emotion. I greatly prefer this over this, or greatly less prefer this than that. I greatly less prefer a messy environment compared to a clean one. So for example, China may greatly prefer CC over DD. Now what happens then with the solution concepts? Remember I said it's moves and counter moves. Well, those different names that I mentioned before, if the sanctions are based upon putting the other player in a greatly less preferred situation, let me say that's a strong solution concept, because the player doesn't want to end up in a really, really bad position. So if all the solution concepts can be strongly sanctioned, the solution concept under consideration, we call it strong. And it may be weak if there's each one UI which is not strongly sanctioned. Well, this is a summary of some of the things that I was saying about preference. I don't think I'll repeat it, but this is once again given in the paper, of course. So solution concept or stability concept, this describes chess-like human behavior under conflict. So decision makers consider the consequences of making a move before actually doing something. So this decision maker will probably only move is ultimately better off. So if all possible moves could result in worse situation, the best choice is to stay. So here's the name on the left, and we qualitatively say what these are about. There's Nash, general mental rationality, symmetric, sequential, symmetric, limited move. We're in a situation, you might have a very clever person who think many moves and counter moves into the future. Or extremely clever, we can think into the infinite future in terms of moves and counter moves. Let's eliminate case of limited move. So all of these things are written down mathematically. And then of course you can program them and calculate them for a given conflict. So let me give you one example of what a definition looks at. So state S is sequentially stable for decision maker I. You'll note by I, S an element of this set here. If and any other. For every unilateral improvement plus there that I has from S, let's call it S1. There exists at least one S2 by the While the other player, if there's two players, I and J,
I can sanction the.
it is less preferred as sanctioned, that's right. And then when you have more than two players, the other players are N minus I, that's a set theory subtraction. All the players except for I. You have to look at all the moves and counter moves they could make together, almost like a coalition. Well, I don't think I'll explain this one here, it's explained in the paper, just to save a bit of time. And then let me just say a little bit about coalition analysis. Can decision makers fare better by cooperation? So a coalition is formed in a given state according to whether or not it's advantageous for decision makers to do so. So we've defined coalitional solution concepts. And one researcher was working with was looking at Pareto coalitional stability. So here, going back to that simple prisoner's dilemma game. Let's see here. This is. If the game moves from state 4 to state 2. If the US goes from not cooperative to cooperate, notice that 2 is less preferred than 4. So probably wouldn't take that move, puts it in the worst position, likewise here, and likewise here for China. Probably wouldn't make a move that's gonna hurt itself. And here, if they move together cooperatively to a joint unilateral improvement, it's better for both of them. So that's really especially a special case of Pareto optimality, a Pareto improvement on it, where both players are better off than nobody worse off. Then we also looked at the evolution of a conflict. How could it evolve from a status quo situation, however you want to define that? And we take a look at the unilateral moves players can make to trace how the conflict could evolve. In some cases, you may wish to look at what if they only use unilateral improvements to move? Well, we can look at that too. And I just showed you this slide here. So psychological factors in power. So I already mentioned hypergame analysis. We also did something with the Japanese, something called attitude analysis. On the Tokyo Institute of Technology, a professor by the name of Takehiro Inohara. We looked at attitude analysis. And you would expect if you have a good attitude towards somebody, it might result in a better result. So any given game, I may have a positive attitude towards that player, a negative attitude towards another, and the other, it doesn't matter, neutral. But we can take that into account. And also hierarchical conflicts and power asymmetry. I've already explained this, so I won't spend any time here. So in most governments in the world, especially countries like France, China, Japan, they have a central government, provincial government, regional governments, and cities. So there's a hierarchy. So in some of the research, we took that hierarchy into account to try to get a more accurate modeling of the problem. So as I mentioned before, the nice thing about a graph, you can store the information in matrices. Did I go through that definition before for sequential stability? Yeah, I did, yeah. That was using Aussie to explain that solution concept. But we can also write down our graph model using matrix algebra. We can redefine all the solution concepts too in that form. It ends up that it's good for designing decision support systems, especially the engines. And it's good for theoretical development. So we had an IEEE paper in 2009 where we first put that forward. And then our 2018 book deals with both the logical and the matrix interpretation format for writing down the graph model for conflict resolution. So we have preference matrices, movement matrices, stability calculations. Now let me move on to what I'm calling the systems perspective model, forward, inverse, and behavior. Well, first of all, let me say we have a lot of theorems and proofs where we take a look at what is the relationship among solution concept. Here we have the set of all states, the big square. GMR is the most general one. So actually, if it's SEQ, it's also GMR. If it's SMR, it's also GMR, and if it's Nash, it's also GMR. I mentioned this existence theorem before. The reason why I stress this one, because we think it's pretty reasonable. Players will only take credible sanctions, won't hurt themselves.
Can I ask a question about that slide? If you go back to that slide,
Yeah.
no, the one about equilibrium. Go down one slide.
Yeah. Okay.
Yeah, so, is the idea that for a theorem or a theory to have a testable proposition, that it has to have a testable proposition, and that the existence of an equilibrium is a real world testable proposition?
Do you mean testable in the real world?
Yeah, so we were talking about why is the existence of an equilibrium important?
Something always happens in the real world. That's for sure, something always happens.
So, but if we're taking a deep complex systems view, we might be living in a non-equilibrium system. And
Well, equilibrium here is different maybe from the way you're thinking about it. I'm not sure.
I guess, could I just maybe ask?
Yeah.
You mentioned the Cuban Missile Crisis as a great real world example.
Yeah.
Can you think of other good real world examples where you see the equilibria from some of your models?
Yeah, we applied it to a lot of real world applications, not just ourselves, but other groups too. Like GMCR2 is used by 122 groups in 29 countries. So we assume that they're also applying it to tough problems that they're looking at.
And do you have maybe your favorite one or two examples of where this model, everyone's always asking us for agent-based models, like, when are you gonna hit a home run, Dawn? When are you gonna hit a home run? What would be like that? So just because we have you here now, I'm wondering if you can remind us of some of your really great home runs from the model.
Well, there's one talk I give on the Iraq conflict that was over the pollution of the groundwater by the chemical company.
Mhm.
And there we got a nice result, and it shows nicely why what happened. And you might remember behind the scenes in the Ministry of the Environment, the company made a side deal. And we thought that this could happen because you could see an obvious coalition could form just from the structure of their preferences. And they did that.
Yeah, thanks. It's just, you've had such a successful career. I think some of the young people in the room don't know that, and just for young people in the room, when you have this case where you have a model and it actually works in the real world, that's a home run, and it doesn't happen all the time. If you have more than one of those in your career, it's really something to celebrate. So sorry if I'm flattering.
Yeah, no, there was one paper, and I've forgotten the title of it, but we did it years ago, about 20 years ago. And we did it while the conflict was ongoing. I think it was happening when the Russian Empire was collapsing. We did an analysis of a certain situation there, and then we actually sealed it, had somebody sign it. And then 15 or 20 years later, we took it out of that envelope, we sent it in for publication. And it did correctly predict what happened. I think it was to the Polish Academy of Science Journal, one of theirs.
Yeah, so it happens. Stick with it, everybody. Sometimes you can make it, you'll be like Keith.
Yeah, and like anything, I think the most important thing is you get a better understanding of the problem. This provides a language of communication. To discuss it back and forth, you do some modeling, some analyses, and then you come up with the result, and you try to think, is there something that can aid in my decision making? If you're a vice president in the company. Yeah. That's why when they computerize it, they use it now, called now decision support systems rather than user-friendly programs. And then for historians, you might ask the question, well, why did this bad result happen when something better probably could have happened? You can reanalyze the situation as it occurred at that point in time. So I think it'd be useful there too.
So it gets this idea also that a lot of the value in building a model isn't getting the answer, but in identifying what your assumptions are and getting consensus on the assumptions and gathering all the information you have about it.
Yeah. Yeah, and obviously what you get from the model, you say that's obvious, well, that's good, that's what you want it to be, it's a good model. I remember once we were doing a little job for a large chemical company from the United Kingdom. We had a bunch of vice presidents in the room. And then we said, well, here's something you might want to consider. I said, oh my gosh, that's so obvious. Why didn't we think of that? You know, just hit their heads like that. So it might point out the obvious, which is good. Just reconfirm that you're maybe thinking well. But probably more often it points out something that you missed. And what you missed might have been very obvious after the fact. And where's some more, what could be done here, Don, is maybe psychologists and sociologists could do some experiments for people where they test this out. Some people did way back, but we're stuck with the real world problem. So we just use large scale case studies.
We can make that work.
Yeah. Yeah, so
Sorry,
that-
I got you a little off track.
no, you didn't. Thank you for that question. That was a good question.
So there's no theorem if it's not intransitive. You have this intransitive preference structure.
No, we have to assume transitivity in that theorem. That's right. Yeah, right, Christopher, you're right. Yeah. But the thing is, if there is intransitive preference present, you can still do an analysis. But that theorem, it might not necessarily hold. But I think getting rid of intransitivity because it looks like it could be messy mathematically is probably not a good reason to do that. You want to have it in your model assumptions that reflect the information and phenomena that's happening in the real world, hopefully, right?
That came up in our last session.
I just wanted to flag we're getting a little bit close to the end of the slot here. We have about another 20 minutes.
Just 15 to 20, okay, thank you.
Yeah. Just leave a
Okay,
couple more.
Okay, then I have-
minutes.
okay, let me mention the systems perspective, because this gets into the future. So normally we go from left to right here. Where are the decision makers, options, and relative preferences? Then we have an engine that calculates stability or the solution concepts. Then we end up with individual stability and also overall equilibrium. Now, equilibrium doesn't mean tranquility and peace. Maybe a better word is compromise resolution, maybe just compromise resolutions. Yeah. Now here, then you might ask the question. So notice there's a question mark here. You're trying to calculate these two. Now, in inverse GMCR, you might ask, well, I have a desired equilibrium here. The question mark here, what are the preferences that are needed by the decision maker to be able to reach that? So that's inverse engineering. That ends up being an AI type of problem because very highly complex and also you get large, enormous numbers of solutions. And then here's the behavioral GMCR. Given the input and the output, what is the type of thinking that took place in the middle here? Now, all these problems, these three problems we've written down theoretically. But then you need really good algorithms in order to apply them in practice because of the complicated calculations and large number of results. We used to have one of the top people in the world here working in inverse engineering, Graham Gladwell. Everybody hear of that name, Graham Gladwell? I mean, he wrote a number of good books. There are mainly mechanical engineering types of problems. His son is Malcolm Gladwell, that famous author in the United States. But he, of course, wasn't aware of this. But I would throw out as a challenge to people here. If you're looking at a certain type of decision technology, let's say a decision system, think about the inverse engineering interpretation of that, the inverse of your system. Because you come up with some very interesting mathematical problems that are waiting to be solved. So here are the behavioral GMCR. Here we don't know what's under the ground. So we know the input, some ground penetrating radar, and we get a reflection here. So given that input and that reflection, what's underneath the ground? Is there an ancient Inca ruin down there, for example, or some buried nuclear waste? So I think I've already described this, so I won't spend much time here. Now, the nice thing about this inverse problem too, if you have some preference information, you can still use this in the model. So there might only be certain parts of the preferences you're not sure of in order to get a good result. And then a nice thing of having a mathematical description of whatever decision system you're working with is that then hopefully you can put together the decision support system so others can use it. And here's a graph of what a good one might look at. So we have the input subsystem, an analysis engine, and output subsystem here. And hopefully that'll provide aids for decision making. So new expanding frontiers. The conflict is everywhere. Even in the definition of sustainable development, you have so-called development or expansion of human activities versus the maintenance of nature somehow, not destroying it. That's a conflict in itself, right inside the concept. And there are many conflicts to look at, and I was pleased that this particular workshop is dealing with climate change, greenhouse gases. But there are all sorts of messy environmental problems going on. Chemicals are the emerging concern, a huge problem. And I like the idea though, of having the practical application give the direction and where to take the mathematics. Because then you get the right assumptions or axioms in your mathematical model. So here's some examples. There are many case study areas that could be looked at. Fish farming, agriculture, sustainable development, climate change, really big ones. That's not here. So lots of room for theoretical expansions, which I mentioned throughout my talk. And in general, not just this model, but I think a wide range model for modeling both the physical systems and societal systems aspects of problems. In system design engineering, we like to think of societal environmental systems because you have to look at them of systems and systems interacting with each other. And you can think of them being inhabited by decision makers within and among systems. So we might want to learn how this decision maker may think based upon how they behave, what are their actions. And can you purposely direct this thinking to win-win solutions? For AI, I guess at the most basic level, can we have machines that think intelligently like people, such as learning and problem solving? And GMCR, inverse GMCR, computer determines how people should think to reach a desirable resolution in terms of preferences. So we think it has a key role to play in conflict analysis. It's extremely complicated calculations and huge numbers of solutions. And then just governors in general, we like the concept of a system of systems perspective. And we want to be integrative and adaptive. A lot of good management techniques come from the field of water resources management, integrated water resources management. We want to achieve desirable system goals such as resiliency, sustainability, and fairness. We hope that'll be present in the systems that we help design or improve or maintain. I just have a couple of light slides at the end here. I mentioned this before, but let me say it again. So Sir Isaac Newton, he was very interested in how do physical models and bodies interact. So he invented calculus to describe the rate of change. So I hope that this workshop here will inspire mathematicians to try to model some of these problems that go well beyond what I was talking about today in order to be able to address this monster called climate change. Now there's the cover of an original printing of his manuscript. I took that picture in the vaults of the Royal Society of London. Has anybody here visited the Royal Society of London? I paid, you did, Chris, did you go down to the vaults and see some of the manuscripts?
No.
Or you missed the best part? Or you went to the Swastika room?
I just went to some conference there, meeting and talks in the big auditorium. I didn't get to see any.
Oh, there's a conference right at that location.
Yeah.
Yeah, you go down to the vaults, And during World War II was actually the location of the embassy of of Germany. And apparently one of the rooms has a big swastika in the floor. I never saw it, but it did go down in the vaults. And that's a piece of the wood that came from the apple tree at Newton's farm. I think many of you have seen the picture. He's sitting under an apple tree, gets hit in the head by an apple, falling off the tree. Aha, gravity. So that's an authentic piece of wood from there. And here's some of his scribbling on his manuscript by Sir Isaac Newton. So it's really amazing to go there. And anybody can go, but you have to book well in advance in order to get in there. But really worthwhile seeing if you're going to London. So I think that's probably a good place to stop. I don't know if there are any other questions.
Okay to have questions?
Oh, absolutely. I think we're just gonna take questions, and if you guys are inspired with any research questions, just put them on the poster board downstairs. And if anyone can read my writing, wrote some things down. But questions, Q&A from the crowd. Is there anyone online? We have. two here.
Yeah, someone joined on the left.
You guys.
I have a question, can constraints in the system be added as conflict and be modeled using this graph theory? For example, can this graph model can be used to model the crop yield and price subject to weather changes?
To model what?
Crop yield and price subject to weather changes. For example, the price of a crop is dependent on yield.
Yeah,
And yield is dependent on the weather changes.
right.
So if the precipitation is very low, we have to irrigate more, which can lead to large scale of groundwater extraction, which is not good.
So you write that down in some sort of causal graph, do you?
Yeah, so can the preference tree that you mentioned earlier be used here to study this crop yield?
I'm not sure about the answer to that.
Okay.
Yeah.
Yes, a question about using the inverse process. So if you, in your, given missile crisis analysis, your prediction for what the outcome would be if the action was to pursue war would be nuclear winter. So in a modern scenario where we're looking at another nuclear war,
You know,
and the predicted outcome would be mutually assured destruction. How can you use that end stage to try to make the decision makers not?
well, you could ask the questions to reach a result where it is a nuclear war. How would the preferences of the decision makers have to change? And then if you know the direction they should change, then you can use practical things in the real world to do it, like some sort of payoffs, right? Like, I'm not sure what happened with Iran and Saudi Arabia. That was nice to see an agreement there. The Chinese really pulled off a major coup. Was there any payment behind the scenes, Costa, to get those two talking to each other? So I think it was tremendous they did that.
Should ask your Chinese friends.
Yeah,
They did this something.
yeah.
You want stability for like the oil flow?
Sorry?
I think like, I know what stability of oil flow. To have peace between them, ensure stability and development, we can have it all, China without it. That's a real benefit.
Did you hear that, Chris?
I heard part of it. So China wants to have stability for their oil flows. So it's beneficial to China to have peace between them.
Right.
And then the last part.
Yeah, regarding, you mentioned Britain and development of capital, but I think a more recent example is general relativity and tensor developed for that. Right, and
General relativity and tensors were developed for.
or it is modeling that relativity. Like Einstein in cooperation with a mathematician as well as the German mathematician, it has been escaped, but, yeah, so.
I wanted to ask, with the techniques you've shown, they seem to be very algorithmic, and you would like compare these ways, you'd find in the preference order a place that's acceptable to both, even though it's not, they're both preferred. Is there all software for all of these processes you've described already in
Yeah.
existence?
Yeah, right now, the system can't do everything I described. It doesn't do the inverse GMCR, for example,
Yeah,
but it does do the forward process.
okay, so if you know all the states and the preferences and either transitive or ordinal ordering, you can do this analysis and then say these would be the stable states or in the equilibria.
Yeah, we can calculate the equilibrium now using a wide range of solution concepts in the forward process. But the inverse one, we've written it down theoretically, mathematically, but it's a nightmare to develop algorithms to actually carry out the complicated calculations.
It doesn't seem that bad to me, but I don't know. I guess I have to look at the the papers. Just-
Well, like, you mentioned like you had a running example of like the escape between China and like the US. And you had a comment that it's, like kind of similar to Prisoners dilemma. And I'm wondering, for that sort of like game, do you have like a hybrid version, like hybrid prison dilemma over many rounds?
Or we play many rounds?
Iterated prisoners.
Iterated,
I think the question is, how does your conflict resolution graph theory model compare to the iterated prisoner's dilemma? Is that the right question? Yeah.
Yeah. I remember Anatole Rappaport had that contest, didn't he? The Anatole Rappaport was somewhat aware of that left branch where I went down in this talk.
Maybe that's a question for a coffee break.
Yeah.
Yeah. It's a question. Thank you.
Thank you so much for this wonderful. Wow. There's
So can you,
for you.
we have a question.
Would you-